Hey, okay, so we're going to be doing problems 57 and 58 from page 211. Alright, so we're given that we are considering the Earth and the Moon as a two-particle system. We're going to want to determine what is the gravitational acceleration at the distance that's halfway between them. Okay? So we're not considering the radius of the moon. We're not really considering the radius of the Earth. We're just considering the distance between them. So we're going to model them as a two-particle system. So we just call these point particles, and then we look at d over 2, where d is the distance between them. Okay? So the first thing we need to do is recall Newton's law of gravitation. And so we're going to let's define which direction is positive. So we'll say positive r hat in this direction. Positive r hat in this instance is going to be going this way. This way. So now, since we want to find g in the middle, let's remember that we have F is equal to ma, right? Which is also equal to, let's just use the magnitude, which is also equal to gravitational constant. Well, we'll say this: gravitational constant times a mass over r squared, where r is the distance between the two objects. And this is going to be, this is our acceleration here. Okay, so this is the acceleration due to the object itself. So what I mean by that is this: we're going to do, let's just use Earth, right? So g Earth is equal to, we're going to say negative, and by the way, this should be negative. So g is equal to negative, g. We're going to say m, mass of the Earth, over the distance between the Earth and the Moon by half, right? We want the distance that's halfway between them. So that's what this is here. Okay, and this is since the Earth itself is pulling gravitationally this way, it's going to be in the negative r hat direction by the way that we've defined it, right? I've set my axis up so that positive r is this way, but Earth is pulling towards it, so it's going to be in the negative r hat direction. Okay, so now let's consider the Moon. So we have something similar. Let's do the similar thing, right? Let's just write it down first. The mass of the Moon over, again, it's the same distance because we're just splitting the difference between the two objects, right? So this is going to be d over 2 because we're trying to find the overall gravitational acceleration at this point. So d over 2 here, d over 2 squared, and now the Moon is pulling gravitationally this direction, which is in the positive r hat direction. So we still have the positive r hat direction here. Okay? So now all we got to do is sum them up. So the overall, we'll call this d over 2, gravitational acceleration at that point is going to be gm, mass of the Earth, over the distance between the Earth and the Moon by half squared. This is r hat minus g, mass of the Moon, over the same distance squared r hat, right? Because we have a negative and a negative, that gives us a positive r hat, and then we have a negative and a positive, that gives us a negative r hat. Okay, so we can also just rewrite this for simplicity this way, and then we'll go mass of the Earth minus mass of the Moon in the r hat direction. And that's really interesting to note that this is really just dependent on the difference between the masses. As far as values for all of these, g is equal to approximately 6.67 times 10 to the negative 11. It was meters cubed over kilograms over seconds squared. And then, let's see, what do we have for mass of the Earth? We have, and by the way, I just looked all of this up. This is all easily found on Google or in any physics textbook. We have 6 times 10 to the 24 kilograms. Mass of the moon is going to be 7.2 times 10 to the 22 kilograms, so it's a couple of orders of magnitude less than the Earth. That makes sense. D, the distance between them, is going to be roughly 3.84 times 10 to the 8 meters. Okay, so now all we gotta do is just plug this stuff in. So it's gonna look something like this. Just do this. 6.67 times 10 to the negative 11. Right? Over 3.84 times 10 to the 8 by half, all squared. This is how I'm plugging it into the calculator. And then we have 6 times 10 to the 24 kilograms minus 7.2 times 10 to the 22 kilograms. R hat direction. And remember the units. We can look at the units here. We're going to have, well, I'll just give you the answer first. It's going to be roughly 0.0107 meters. Let's do units now. So we have meters cubed over, what is it, kilograms over seconds squared. This is going to be this is kilograms, so kilograms goes away. And then we had, what did we have here? This was distance. This is meters squared, right? 1 over meters squared. So that gives us meters per second squared. So we're looking at roughly 0.011 meters per second squared. That's the answer. I should note that this, actually I wrote this as a vector, so I actually should include this. This is really important. R hat direction, right? See, because I wrote it as a vector, and here is my unit vector. Okay, so now it asks to find the magnitude of the gravitational force. Is that right? Yep, okay. 57b says an asteroid with a given mass, is at the point exactly halfway between the Earth and the Moon. What is the magnitude of the gravitational force on it? So we figured out what is the gravitational acceleration at that point, halfway between the Earth and the Moon. Now we're given a mass. So the mass is 6.69 times 10 to the 15 kilograms, so a pretty gigantic asteroid, times the gravitational acceleration that we're given. I'm just going to plug in the exact number that I found, meters per second squared, and that's going to give us units of newtons. And this gives us 7.1583 times 10 to the 13, 3, 6, 9, 12, 13, which is going to give us, I could say this is still approximately equal to 7.16 times 10 to the 13 newtons. That is the gravitational force on it. And remember, it's positive r hat direction because of this. Oh, since it's asking for the magnitude, we don't actually use it as a vector. So this is the answer. Okay. Notice that I wrote this here wrong. 13, that's what we're asked to find. It is worth noting, just before we move on, that if you plug in this value versus this value, you'll get a slightly different answer. So if you plug in 0.011 times 6.67 times 10 to the 13, you'll end up getting roughly 7.36 times 10 to the 13 versus 7.16 times 10 to the 13. So that may affect your answer in the homework, so be careful of that. The next problem, number 58, we are given that the moon and the Earth are a two-particle system again. Okay, so here's the Earth, and here's the moon. Oops. This is the moon. It's a dot. Okay, it's asking us how far from the center of the Earth is the gravitational field of this two-particle system 0. Okay, for this one, since we don't know the distance, because before we were just told that we wanted to figure out what it was at d/2. Now we want to figure out where is g equal to 0. So we have this distance here. We'll call this distance r. We have this distance here. We'll call this distance d minus r, because the total distance, recall, is d. Okay, and so this point, since we can kind of shift this point around to try and figure out where this is going to be 0, we'll call this d minus r. So this is whatever's left. This is d, this is r, and this is d minus r. Okay, so this is going to make it a little easier in the long run. Let's do it this way. So now we want g, mass of the Earth, over r squared, right? Because the distance we're saying here, this is going to be r. Here's the mass of the Earth, and this was also negative in the negative r hat direction by our convention that we defined earlier, where r hat was in this direction. So that makes it positive. So this is going to be g m Earth r squared r hat. Okay, and next, so g, we'll call this g of Earth, and then g of the moon is going to be, well, it's going to be g times the mass of the moon over the distance that we set up to the point, right? So here's the point, here's the moon. This distance is d minus r, so that's what we use, d minus r squared. Okay, now let's sum those up. So we get g m Earth over r squared. I'm just going to use the magnitudes instead of the vectors right now. So this is going to be this here, d minus r squared, and remember, it wants to know where is this equal to 0. So now that means that we just solved, right? So we have this all equal to 0. We can just pretty much put the equal sign here in the middle. Like this is equal to g, mass of the moon, over d minus r squared. Okay, I'm just solving. All right, so now this cancels, right? What we're solving for here is r, because we know the distance between the Earth and the moon already. That's a constant that is known. Okay, so let's take the r to the other side. So here, let's take the ratio, since that's how we have to solve it. Right, so that means that now we have this square root of the ratio of the masses between the Earth and the moon is equal to this. And for the sake of brevity, I'm just going to introduce a dummy variable. We'll call it alpha, because this is just going to make things a little easier as I go through the calculation. And then I'll return it at the end. So this term here, I'm just going to call alpha. Okay? So now I'm going to take this to the other side. So d minus r times alpha is equal to r, right? So that means that d alpha minus r alpha is equal to r, which means that d alpha is equal to r plus r alpha, which is d alpha is equal to r 1 plus alpha. Okay, that means that r is equal to d alpha over 1 plus alpha. Way to rewrite this is, let me check this. Another way to rewrite this is going to be, we can just call it d alpha over 1 plus alpha, which is also When you're doing the calculation, trust me, this will make it a little easier. I mean, it did for me. You can always just plug in the numbers at this point and see what you get, because remember that alpha is just a dummy variable for this. So plug this in for alpha. Here, you could just solve it. I like to make things a little more visually simple before I move on. So what I do is I set it up like this. Okay. That's a fun algebraic exercise. If you don't know exactly how I did that, I encourage you to try it. All right. So the distance between the Earth and the Moon is 3.84 times 10 to the 8 meters. Okay? And then we have 1, let's just call it like this. This is going to be, it's 1 over this term, so that means it's square root of m naught over m Earth plus 1, oops, that's not a 1, plus 1, like that. So then I plug all of this in and see what we get. Okay, so I came out with 3.46087, more stuff down here, times 10 to the 8, or approximately equals to 3.46 times 10 to the 8. Exactly, pretty much what's written. And this was, so this is just in meters, because we're looking at distance. Here's meters, these cancel, yep, so we're in meters. Okay, and that's going to be the distance. This is the distance from Earth where the gravitational acceleration is equal to 0. And also this is what's known as a Lagrange point. This is Lagrange point 1, or L1. Part B for 58, we're asked to sketch the gravitational field. The field vectors, G, along the line joining the Earth and the Moon, indicate where G is equal to 0. Okay, so pretty much, I already drew the picture once, but I guess to be explicit, and since we're asked to do it, let's do it again. So remember that this is our distance between the Earth and the Moon. Right? These are point particles because we're asked to model it as a two-particle system. And so, know these values. This is 3.84 times 10 to the 8 meters. Right? And then our value, where this was 0, was all the way 3.46. So it's going to be, and this is times 10 to the 8 meters still, so this is going to be way over here. So I'm going to say that this is our Lagrange point, L1. And this distance, let's use a different color, purple. This distance here is what we found. This is going to be, if I can get this to straighten out, this is going to be 3.46 times 10 to the 8 meters. Okay? If we subtract those two, we can actually have a distance here. Not that we're not explicitly asked to find this, but it's good to kind of have a visual of what we're doing. So if we plug this into a calculator, 3.84 minus 3.45, all times 10 to the 8, you get 3.84 times 10 to the 7. So that's what this is, 3.84 times 10 to the 7. So still quite a bit of distance, actually, between the Moon and this point. So I would say that this is not to scale. But anyway, we're asked to draw where G is equal to 0, right? So G here is equal to 0. And then, so now we have, well, let's erase this. That's not really helping right now. So we're going to say, we're going this way because we're asked to sketch the gravitational field vectors along the line joining the Earth and the Moon. So that's going to go here. It's too big because this is 0, right? So we want these to be roughly the same. Let me just fix some of this because this is kind of, there we go. Let's make this much larger. Good. Okay, that way we can sort of identify these vectors a little easier. These need to be roughly the same size, so what I'll do is I'll just copy this, because I have that ability. Alright, there we go. This is where they cancel out. This is where g is equal to 0. So that's the answer for that problem. Which, it's not really an answer, they ask you to sketch, and that's what we get. Next problem. I just noticed that this wasn't quite long enough. Okay. Alright. 12, 13, and 14 on page 240. So we're asked to consider which objects need to be included in 3 cases, right? So we have, the first case we have height and a ramp. There's a ball. Case, this is number 1. Number 2, we have, I'll just draw it. Case 2, we have this ramp with a ball on it. This is going to be the initial point, and this is the final point. And then 3, same situation, but these are different heights, I believe. But I don't know if you can hear that. There's thunder. Yesterday we had fireworks. Today we get thunder. So what it wants to know is like which things are included in the system. Okay. So pretty much in all of these cases, since we're considering gravitational potential energy, we need to consider the Earth, right? So these are all on some platform of the Earth, right? We're going to be including the gravitational acceleration from the Earth. Recall from last chapter that it was actually looks something like this, where r was the radius of the Earth. Okay, this actually should give you about 9.81 meters per second squared. Okay, so since we have to consider that, pretty much in each of these cases we're going to consider the Earth. And since we have a ball, we need to consider the ball in every case. Since we have a track, we need to consider the track in every case. Now, one thing to be clear about is I don't actually know if, in considering this as one track, is this different than considering this a track. So I guess what I'll say is this is a ramp. Earth, ball, ramp. We need to consider that for case 1. Then we need to consider Earth, ball, and then I'm going to say track. I don't know if this is ramp and loop. If this shows up on the homework, that might look something like that. So you would need to consider both of those, but I'm just going to say track here. Okay, so that's pretty much the answer to number 12. Calculate the change in potential energy and gravitational potential energy for each case. So let's draw number 1 again. Right, this is, what do we have? This is some angle. We have a ball. We have a height. This is height h. Over here. This is all in the book, by the way. This is the initial position. And this is the final position. It's down here, right? The ball has a mass m. So in the chapter, if you read the book, it tells you that potential energy is path independent. That means it doesn't matter how this ball gets from here to here. All we're really considering is how much gravitational potential energy does it have up here and how much does it have down here. So at the top and the bottom. So what we do is we set this up. Delta U, the change in potential energy, is going to be U final minus U initial, where U is your gravitational potential energy, and this is, we have mg 0, because we're going from height h to 0. Let's just define our 0 axis down here, right? Minus mgh. So what I'm saying is this has 0 gravitational potential energy at the bottom. This is y equals 0. At the top, however, where y is equal to h, we have mgh. And since we're taking uf minus ui, where this is initial, this is final, right? So we have 0 minus mgh. So that gives us a total of negative mgh. 2. So we have this height here, 5/2 r, and then we have this track with a loop. This loop, I'm sorry that it looks so terrible, that's a bad drawing. This is r. Final position is b, right? So we'll call this final. This ball has mass m. This is initial position. And we want the change in the potential energy, right? So, since this is r, the radius of this loop is r, let's consider it to be more of a perfect circle like this, right? Since this is r, this height that this sits at is going to be 1, 2r, okay? So this final position here is actually m times g times 2r. The initial position, since we're sitting at 5/2 r, is going to be, let me just redraw this because this looks too similar to the one that's in the next part of the problem. So what I'm going to do is I'm going to take this real quick. I just don't want it, I don't want there to be any confusion. Okay, so that's 5/2 r, this is 2r. Alright, so I think that's a little more clear. Because we're actually going down. This is a much taller height than this, right? This is 2r, this is 5/2 r. We know that this is greater than 2 because it's not 4/2 r. Okay, so what I'm saying is delta u is equal to mg, well, it's u final minus u initial. So it's going to be mg 2r minus mg 5/2 r. That's our height at the initial. Okay, and then we just solve, right? mgr, this is how I would do it, but you're going to have, actually, you're going to have 4/2 because it's 2. I'll just be more explicit. Just solve real quick. 4/2 minus 5/2 r is equal to mgr times negative 1/2. So this is negative mgr over 2. That's delta u. Next part, we have a very similar situation, but it's just a little different. So here we have, this height is 2r. And we're going to go down a ramp, and then we're going to be into the loop again, right? Here's the loop, here's initial, here's final. Remember, this is still the same, this is still radius r, so this is mg2r, that's our final gravitational potential. And our initial is also, since we're at 2r, mg2r. So, since we have uf minus ui, now before I do that, I want you to recall that, again, I mentioned that from the chapter that the change in potential energy is actually path independent, so it doesn't matter how you get from one place to another. What matters is what is the potential at the final and initial positions. So here, this is mg2r, and this is mg2r, and so that really, it pretty much puts you at 0. There is no change, no overall change in the potential energy from the initial and final positions. If you were to consider this ball down here, there would be a change in potential energy, but since it would go down here and then it would go back up here, it would still be 0 overall. Okay, that's the answer. Next problem, number 14. We're actually given values that we just plug into the expressions that we found. Okay, so then what was the first one? Delta U for case 1 was negative mgh. So we pretty much just plug that in. need to go through all of the steps because I'm just using a calculator, but we write this down. So case 1, delta U is equal to mgh is equal to what is given to us is I was just looking at this here, and we're given an angle, but we don't actually need the angle, so I think that's there to trick you, I believe. So we have a mass of 0.65 times gravitation constant meters per second. This is in kilograms, by the way, so I'll write that at the end. I'll just put it here. Times h is given as 1.35 meters. The only way that you would want to consider the angle for this problem is if you're considering the path. So if you wanted to know something about this, right, then you would use the angle. But since it's path independent, all we need is the height. We just need to know what is potential here and what is potential here. So we should be good there. Okay, so you do this and it comes out to be, let's see, I have it here. .6. You have 8.6, and the units are going to be kilograms meters squared per second squared, which is actually a joule or a Newton meter. But we're going to stick with energy. Units of energy is a joule, so it's negative 8.6 joules. That's the change in the potential energy when the ball comes down the ramp. Okay, number 2, we're given, what was this? It was negative mgr over 2, right? I think I got that right. Yep. And so we have negative 33.5 over 2. And we have 756 kilograms. And then we have mgr 9.81 meters per second squared. This was meters. I just put that in half. It doesn't really, because 2 is unitless, it doesn't really matter. And this is going to give us energy here is going to be negative 12, oh shoot, 124,224.03. This is going to be in joules again. Let's use J, or we can say 1.24224. You know, depending on how you are asked to do your significant figures, you can round it somehow, right? I'm just going to include all of it. So we have 1, 2, 3, 4, 5 times 10 to the 5 joules. That's a lot of energy, but recall, I mean, especially when you compare it to the last one, this is order of magnitude 10 to the 5 joules. When you compare it to the other one, it was just around 10 joules. And this is negative also. So why is that? Why are these so different? Well, the reason is because we're going a much greater distance and we have a really heavy ball, right? So, or a more massive ball, I should say. 756 kilograms here versus, what was it? Like half of a kilogram here. So there's a much greater change in energy. And for number 3, it doesn't really matter what the mass of the ball is. The answer is still going to be a transfer of 0 joules, just because you can plug whatever you want in here and you're going to get 0, right? Okay, next problem. Number 16 on page 241. We are given some blocks and a pulley and an incline, right? So let's just draw a quick picture. Here we go. We have the 2 blocks on the incline, and I've shown that they are at the same height initially, right? And so we're told that this block on the left, this one over here, is going to go down a distance of h, right? That means that this thing is going to be pulled up an equivalent distance of h because they're connected by a rope. So if this travels down a distance of h, it's going to pull this rope a distance of h, okay? So let's start setting this up. Make it a little bigger so we can see, because it's going to get a little cramped. There we go. All right, so let's draw our distance of h. And then we're going to say that this distance of h is the same, just like I mentioned before. Okay. And now what this is telling me already is that we're going to have some triangle. Well, we do have a triangle because we're given an angle, and this is a ramp, right? So this is going to be, from trig, we can just kind of consider what h is going to be in terms of the angle, right? So I just drew it facing the other way, but this is some height. So this thing is being pulled up a distance of h along the ramp. So it's going to go like this. Now y is going to be equal to, I can draw this if I don't have enough room. So y, the distance that we're changing in gravitational potential energy, remember this is path independent, right? So it's going from one position where it has a specific gravitational potential, and it's being raised up to another position where it has a gravitational potential. So that distance that's being raised up, we're going to call y. This is x. We're not really going to consider that. So now y is going to be equal to h sine theta, right? Just from this alone. This is h sine theta. Okay? And so that's what we're going to consider when we talk about the change in the gravitational potential. A couple seconds to extend this a little bit. So you can see that now when this thing falls a distance of h, there's still some distance left. And so what I'm saying is that what I'm claiming is that this total distance here, that these things are above the ground, since they're both at the same distance from the ground initially, this distance is L. Okay? And so what's going to be left after this point here is L minus h, right? So this is L as well. So the initial height here is L. Okay, now what happens is actually really cool. If we were to consider L as 0, which you could possibly do, it'll take one less step. But I'd like to show this just because you may come across a problem where you're going to need this. Consider for block 1, M1 here, what is the change in gravitational potential? So U is equal to U final minus U initial. And so U final is going to be, this thing comes down here, it moves a distance of h and it comes down here. Now we're at a distance of L minus h, right? So M1G L minus h, okay, minus the initial, which is going to be here, M1 times G times L. That's where we're sitting. This distance is L. So M1G L. Okay, so that means that we have M1G times L minus h minus L is equal to negative M1GH. Just, it's only dependent on the distance that it's changed. Well, that's really all we're looking for, is the change in potential anyway, right? So that makes sense. Let's find the change in potential for the mass 2. UF minus UI. So what is UF? So UF is going to be, well, let's look at our incline real quick. So this is going to move up a distance of h, right? But we said that this actually moves up, straight up, since we're only considering the gravitational potential. This is going to move up a distance of y, which is h sine theta. But it also is L, right? So it's going to be L plus h sine theta, right? So to be more explicit, M2G times h sine theta plus L minus the initial position was just M2G times L. So what does that mean? It means that the change of potential has gone up a value of h sine theta, and that's it. To be just more explicit, in case you didn't catch what just happened, M2G h sine theta plus L minus L. Okay, and that gives you this answer here. So there you have it. The overall change in the potential for block 1 is negative M1GH. The overall change of the potential for block 2 is M2GH sine theta. So problem 24, we're given two scenarios. Let's just go down here. 24 scenarios. So I just drew the picture real quick. So we take this spring, it's uncompressed here. This is case 1 and this is case 2. We place this block on it, and in case 2, it's compressed because this block has mass and it pushes it down, right? Due to gravitational potential. Okay, so what it's asking us to do is part A. What must be included in the system? Well, we need the mass, or the block. We need the spring. That's important. And we also need the Earth. Because without Earth's gravitational potential G, without Earth's gravitational acceleration G, none of this is really going to make any sense. Okay? And then part B. So that's part A. So that's part A. And then part B, find an expression for the change in the system's potential energy in terms of the parameters shown in. So now we're just looking for an algebraic expression for the change, for the total change in the system's potential. And then in part C, we plug in some numbers. Okay, so let's start. What we're going to do here is we're going to use conservation of energy. We're going to consider this as an entire system, right, with the Earth included. So this is a whole system. And we're going to say that the energy initial is equal to the energy final, right? So the total energy of this closed system doesn't change. Okay? So what is the initial energy? Well, we have no kinetic energy. We're only looking at potential. So in situation 1, the block is rested on an uncompressed spring. So this spring has no displacement right now. It's just sitting perfectly naturally, and this thing is almost touching it. We can really zoom in and make that a reality if we want. There we go. Let's try it a little bit. There we go. So we're almost touching the spring. Okay, so what we have is we have half k, and the displacement is 0 squared, right? That's the potential of the spring. And then we have m times g times h. Also, the reason I'm using h is because in the book, in the diagram, it shows that this thing moves a value of h. So from here to here, this is h. Yeah, it's kind of a mess. Here, let's try again. From here to here is h. Okay, so that's why we're using h, because this is only going to go as far as the spring will allow it. So this is the maximum gravitational potential at this point. So now, once the spring is compressed, this thing doesn't, we're going to consider this our 0 point, and this thing doesn't have any more gravitational potential because it's resting on top of the spring, right? Okay, so now our final, this is E initial. Now E final, since I just told you that the mg, and then this thing went down to 0, right? This went from h to 0 here. So we're going to consider that 0. And then we have this displacement is actually h. So this spring moves a distance of h, right? So the spring is displaced. So here's our spring potential. If any of this is unfamiliar to you, it's in the book. So this is h squared. Okay, so now we use our equation, EI is equal to EF, which means that we have mgh is equal to 1/2 kh squared. So I think I've added an extra step, but what we can do here is this. We can say the total change, we're just looking for the change in the potential. So the total change in the potential, we can use EF minus EI, which in our case, since we don't have any kinetic energy, we're considering is just going to be UF minus UI, and this is going to be U final for both blocks, right? So U final for both blocks is mg0, for mg0 for the block, and 1/2 kh squared for the spring, right? So that's final. And then for initial, we have mgh for the block and 0 for the spring, which means that the total change in potential energy is equal to half kh squared minus mgh. Okay, and now we go ahead and we plug some numbers in for part C. Before we do that, I just want to point out that this part using conservation of energy wasn't completely necessary, but it can actually get you to the answer. What you could have done was just start out directly from this equation here, right? Or what we've used before, ui minus uf minus ui. So if you just start here, this will get you more quickly to the answer. Okay, so I just had like an extra line of math. So, all right, so let's just plug in some values. So what do we have? We have half k is 125 newtons per meter. That's a mess. 125 newtons per meter. H is 0.065 meters. That's squared minus mass. What was it again? Mass is 0.865 kilograms times gravitational constant times 0.065 meters. Okay, so I'm going to plug all that into the calculator and see what we get. With approximately negative 0.2876 joules. So you can round that however you want. It depends on which significant figures you're asked to find, but I mean you could say it's approximately 0.3 joules. It's pretty low, actually. But we're dealing with something it's an incredibly small distance. I mean, this is what, 6 centimeters, and then the mass is not even a kilogram, right? So that makes sense. Number 26, we're asked to do a very similar thing, but this time the springs are inverted. Okay, so it looks like we're given similar values for everything. And I've drawn the picture, right? Here's our ceiling. Here's our uncompressed spring, excuse me. This is a spring, not compressed or stretched. Here's a block we're just about to hang it on there. So exactly the moment that we hang it on here, this is initial, right? And then this thing is going to stretch and come down, and this is our final. So it wants us to calculate the change in potential energy just as we've done before. So we're going to need the potential for both, for two parts, right? Because we're including the block, the spring, and planet Earth down here. Okay, so let's do the block. So here at final, this thing has traveled. We'll call this our 0. Since we're starting here, we'll call this 0, right? And this thing has traveled. Sorry, that's backwards. We're still going to call this height h, and this is our 0 down here. This is 0. So this thing starts at h and comes down. So final for the block is mg times 0. And then final for the spring is going to be half k times the displacement, which in this case happens to be from here to here. This total displacement for the spring is h. So this is looking pretty similar to what we did last time. So that's the final energy, right? The initial energy here, the spring is unstretched, uncompressed. There's no displacement for the spring. So this is going to be half k times 0 squared plus this block. Now we know it's not going to travel up. We know it's going to travel down, and it's going to be contained by the spring once it goes down here. So this is going to start here and travel a distance of h. So this is going to be mgh. Okay? So total change in energy is very similarly half k h squared minus mgh. I don't know why I wrote squared. That's not right. Minus mgh. There we go. That's your answer. And then it's the same thing as last time. So when you plug it in, you get the exact same answer, right? Because this is what we started out with. This is the same answer, which is really interesting. because it depends on how you define your axes. But I mean, the total change in energy is what we're after, and the total change in energy for this system here is the same as the total change in energy for this system. We're just turning the spring around, okay? And we're given all the same values. So this was what? It was 0.2, what was it? It was 0.2876, 2876 joules. So that's your answer. All right, thanks. Till next time.